ELEC1 2020 question 2, part A. Simplify the following Boolean expression using a Carnell map. Justify your answer by showing and identifying any groups you make. And this is worth 4 marks. Now those 4 marks are for populating the Carnell map with your highs, and then the second mark is for identifying the groups, and then labeling those groups with the third mark, and actually giving a final expression for Q equals will be the final mark. Okay, so let's deal with the first expression. D and not C and not B and not A. So D is high and C, B and A are low, and so that would give us a high down here. And then we've got D and not C and B and not A. So D is high, C is low, B is high, A is low. So we're looking for a 1, 0 for DC and a 1, 0 for BA. So that's this bottom right hand corner. And then we've got not D and C and A. That means B doesn't matter. So B can be both high and low. So we're looking for D to be low, C to be high. So that's the second row down. And then A to be high. So A is high, and that these two positions. And then finally, we're looking for D and C, and that means we don't care about B and A. They can be both high and low. So we're just looking for D and C to be high, and that is the entire third row. Well, let me just go back. There you go. So it's the entire third row. Now what we've got to do is we've got to recognize the largest groups. And the largest groups, well, you can hopefully recognize quite quickly a 4 in the middle. So we've got one group there, and then that leaves us another 4, and they can be grouped by 2 either side. Now we've got to label these. Now this middle group is C and A, and the group out to the side, this is D and not A. And so our final answer, Q, is equal to C and A, or D and not A. Okay, part B. Use Boolean algebra to simplify the following Boolean expression. Now you might look at this and go, I know what the answer is immediately, and it is worth 2 marks. But the problem is you've got to show your working in order to get both marks. And I'm going to go through step by step, because obviously there will be people who won't see the immediate answer as far as this is concerned. So, easiest way to do this is to basically bring the A and B and the A and not B together and stick an A outside a bracket so that we've got B or not B inside the bracket, and then we've got or A. Well, B or not B is equal to 1, so we're going to have A and 1, or A. A and 1 is A, so we've got A or A, and hopefully you know through your Boolean identities that A or A is equal to A. Okay, part C. Use De Morgan's theorem to simplify the following Boolean expression. Now the key as far as this is concerned is to remember to retain the brackets. Okay, so hopefully you recognize that it's the OR gate here that we've got to use in order to make our separation, and that's where we're going to divide that not line. Remember, when you do De Morgan's theorem, try and work from the outside in, so the largest expression, and work down to smaller expressions. The tendency is to try and maybe break things up from the inside, but no, work from the outside in. So we're going to look to divide that line there, and that OR gate expression is going to turn into an AND gate expression. So we're going to end up with Q is equal to A or B, all knotted, but we're going to keep that bracket. Then we've got an AND, because the OR's changed from AND, and we've got not B. And then that top line is then split into 2 separate lines. So we're going to end up with the not of A or B and and then obviously we've got the final part. Okay, so now I've actually missed out a expression there, and you've got to be careful that you don't do this, and make sure that you don't make mistakes. So what we've got is that, because it will impact your final answer. So we've got A or not B, all not knotted, and it's and the not of B. Right. So that not of A or not B cancel each other out. So we're going to end up with A or not B. But again, we retain the bracket, and the not of B is just B. Now we've got to retain that bracket because we now need to expand that in order to get the correct answer. So the expansion of this is going to be A and B, or not B and B. And that is equal to A and B, or, now your Boolean expressions for not B and B, hopefully you know that that is 0. And again, from your Boolean identities, anything or 0 is whatever the other thing is. So that is going to leave us with A and B as an answer. Okay, part D. For part 1, complete the truth table for the output queue of the multiplexer circuit shown below. Multiplexers are fairly straightforward as long as you remember that the outputs are determined by the attachments to whichever power rail, the plus or the 0 that they're attached to, and that 0, 0, 0 is D0, and the bottom one, 1, 1, 1, is D7. So as long as you remember that, then hopefully things will be fairly straightforward. So when we're looking at the outputs as far as this is concerned, D0 is attached to the 0 volt rail, and then 001 is a low as well. And then we've got 2 highs, we've got 2 lows, a high and a low. And it's very quick once you recognize which attachment is where. Okay, part 2. Determine the simplest expression for output Q using a Carnell map or the rules of Boolean algebra. Well, I'll do both because if some of you might use Boolean and prefer Boolean, others will prefer Carnell maps, and hopefully you should end up with the same answer. So if you're using Boolean, then you're going to end up with this expression as a starting point. Okay, so not C and B and not A, or not C and B and A, or C and B and not A. Well, hopefully you can recognize that we can link the two expressions at the beginning together, and I'll do every step just in case you're not confident as far as this is concerned. Now in that bracket we've got not A or A, and that is equal to 1, and so we'll end up with not C and B and 1, or C and B and not A. And anything and 1 is whatever that anything is. So for that particular part of this question, I do apologize, let me just go back. Right, so we've got not C and B and 1. Well, that will give us just not C and B. And we've got C and B and not A. And then, as far as that's concerned, we've got to take the B's out now. Okay, so let's take the B and stick the rest in a bracket. And we're going to end up with B and bracket not C, or C and not A. And that bracket, we can use some redundancy theorem, and we'll end up with B and bracket not C or not A. And You might think, well, I'll keep it at that, but the reality is that would involve 4 gates. You've got 2 NOT gates, an OR gate, and an AND gate. It can be made slightly simpler by using some De Morgans, and hopefully you recognize that in that bracket that can be changed into the NAND C and A, and that would just be 2, and we could, if we wanted to, just to make sure that we're separating out the parts, we can see we've got a NAND gate there and then an AND gate with B. Right, we should be able to do exactly the same using De Morgans, using Carnell maps. Now, if you fill out the Carnell map, hopefully you'll end up with these 3 areas being high and everything else being low. As we did it in previous question, you've then got to recognize the groups. We've got a 2 here, and we've got a 2 here. Now that first 2, C doesn't matter, so it's just B and not A. And in the second group, it looks like A doesn't matter, so we're going to end up with not C and B. And therefore, Q is going to be not C and B, or B and not A. Well, that means that can be simplified further into B and not C or not A. And as with the Boolean expression, that can be turned into a NAND gate. Okay, part 3. Design a logic system to generate the same logic function as the multiplexer. Well, you can go all the way back and do this, or you could, if you wanted to, try and draw the individual expressions. So the top one is the one that the mark scheme would suggest you should at least be able to get to. So if you have B and not C, or B and not A, you should end up with this as your final circuit diagram, and that would be worth 3 marks. If you ended up with B and bracket not C or not A, you should end up with this as your final circuit diagram. You can see the difference, less gates, this has only got 4. But if you ended up with B and the NAND C and A, you end up with just 2 gates. So this should be your final circuit diagram. And this concludes question 2.